We are going to talk about that problem 2. So we're still working on 3D.1. It is a mammoth exercise, but we're going to crank through this question today. And hopefully you're seeing 3D.1 is just a real consolidation of increasing, decreasing, stationary points, and now the concave up, concave down. It's bringing all of those things together, preparing us for 3D2. So let's get into this question. We've got x squared e to the x, and it says discuss as x approaches positive and negative infinity. Okay? So there's two ways we can go about this. The first way is to just have a look at the graph and see what's happening. What happens as you go really far to the right? As x increases, what's happening to the y value? We can see it's shooting up, and it's just going to shoot up and out forever. So we're going to make a statement as x approaches infinity, y approaches positive infinity. And then what happens as x approaches negative infinity? As it goes really far to the left, what's happening to the x value? And it's just an asymptote at 0. It's getting closer and closer to 0. I'm going to make a mathematical argument as to how we generate those up here. Okay? So let's first discuss as x approaches positive infinity. And so what you're doing then is you just choose a really big number, like x is 1,000. What we're going to have is 1,000 squared times e to the power of 1,000. Now remember, e is just a number. All right, so we're going to have 1,000 squared times by 2.72 to the power of 1,000. And what does that mean? It means, let's make sure I don't put too many zeros here, too many there. 2.72 times 2.72 times 2.72, 1,000 times. All right, so you can see this is just getting astronomical, and it's just going to keep getting bigger and bigger. It doesn't matter what the number is you put in, as long as it's positive, that it's just always going to get bigger. Okay, so that's going to be our first statement, is as x approaches infinity, y approaches infinity. Okay, as x gets large, y gets large. Okay, what about as x approaches negative infinity? So let's choose a really negative number, like negative 1,000. So let's say, x approaches negative 1,000. We're going to have minus 1,000 squared, all right, times by e to the power of minus 1,000. So what we've got there is a big number, because it's going to be positive because it's squared, and then we're multiplying that by 1 on e to the power of 1,000. All right, so it's 1,000 squared times 1 divided by 2.72 times 2.72 times 2.72, 1,000 times. So you've got 1 divided by this astronomical number, okay, 2.72 to the power of 1,000. So what this is, this part here, let's talk about this part here. This part here is like if you have one cake divided by 7 billion people, everyone's getting like a crumb. Everyone's getting pretty much nothing. This part's approaching 0. This is getting closer and closer and closer to 0. So it doesn't matter how big this number is, we're multiplying it by 0. And so it's getting closer and closer to 0. And so we're going to say as x approaches infinity, y approaches 0 from the positive side. Okay, it's positive y. All that means is it's above the x-axis and it's getting closer and closer to 0. All right, could be below the x-axis and getting closer and closer to 0, in which case it would be approaching 0 from the negative side. Okay, so that's part A. Any questions about that? So look, when asked something like this is worth 1 mark, okay, or maybe 2 marks. All right, if you're making 2 statements. So there's no working out required. All right. So this is how you can think about it, But ultimately, you can just look at the graph and say, what's it doing? What's it doing for big values of x? Zoom right out and have a look at it. Okay? So part B, find f dash of x and draw a sine diagram. So if we have f of x is x squared e to the x, we're going to have to use the product rule. So we've got u is x squared. And f dash of x will be okay. You can draw its sine diagram. X e to the x times 2 plus x. Okay, so here, if we're going to draw a sine diagram, we want to know the roots, we want to know the values for x. So we can rely on our calculator and just graph that and get the sine diagram from it. I'm going to try up here, do it manually until I really have to rely on my calculator. So if we want to draw a sine diagram, we're going to need to know its x-intercepts. All right, they're going to occur when that equals 0, and we're just going to apply the null factor rule. We're going to have x equals 0, e to the x equals 0, or 2 plus x equals 0. Okay? If we have these three things multiplying together to give us 0, then either that's 0, or that's 0. Now, e to the x can never equal 0. E to the x does not equal 0. Remember, the graph of an exponential function is asymptotic to the x-axis, so an exponential will never be equal to 0. So that means these are our two solutions. X is 0, or x is minus 2. So we've got minus 2, and we've got 0, and then we need to indicate where it's positive and where it's negative. Okay, so let's do it. Let's make a sine diagram with a mathematical argument. Okay, let's do that. So we've got let's choose a number between minus 2 and 0. We're going to say when x is minus 1. What's the value of the derivative when x is minus 1? It's going to be minus 1 times e to the power of minus 1 times by 2 plus minus 1. 2 take 1. So that's f dash of x. Okay, that'll be minus 1 times 1 on e times 1. Alright, and so this is just going to be negative 1 on e. The significance is not the value, just that it's negative. In this region it is negative. Okay, when we put a positive number in, when x is positive 1, we're going to have 1 times e to the 1 times 3. That's going to be positive. And when we put a number left of negative 2 in, like if we were to put negative 3, we're going to have yet a negative times a negative. So it's going to be positive as well. All right, so I've generated the sine diagram without the calculator. Now the sine diagram, let's make some statements about it. So find f dash of x, draw a sine diagram. C, hence state where it's increasing and where it's decreasing, okay? Therefore, remember this is a sine diagram of f dash of x. Therefore, f of x is increasing or x being less than negative 2 and greater than 0. Decreasing in between those 2 points. Okay, we can see that from the sine diagram. That tells us when it's got positive slope. Okay. D, hence state the coordinates of any stationary points. Well, we've got a local max at x is minus 2. Okay, it's increasing and then decreasing, and a local min at x is 0. Okay. Local max at x is minus 2. We need to find the corresponding y value for those points. Okay, so we say, well, what is the y value that corresponds with minus 2? Now we're talking about the original function, because we're looking for a coordinate on the original function. So when x is minus 2, we're going to have minus 2 squared times e to the minus 2, which is 4 on e squared. And when x is 0, we're going to have y is 0. So local min at 0, 0. Local max at x is minus 2. Y is 4 on top of e squared. Remember, 4 on top of e squared is just a number. We could calculate it to a few significant figures. Alright, so that's first page done there. A, B, C, D. And look at that on our Desmos here. I've decided to use Desmos today. You can use your graph calculator just because it makes a bigger graph. And you can see that local max there. X is minus 2, y is 0.541. So there you go. 4 divided by e squared is 0.541. And then that local min at 0, 0. Okay? Now we're going to anticipate, before we answer the next part, where it says find the second derivative, draw a sine diagram, hence find any points of inflection. There's a point of inflection somewhere in between here. Okay, see where my mouse is at the moment? Because it changes from being concave down to concave up. So there's a point of inflection in there somewhere. And I reckon there's even another point of inflection around here somewhere. We can't see it very well because of the y. Let's change the y and see if we can see it a bit better. Let's go from minus 2 to 2. Alright, very good. So we can see, here it's concave up, alright? Sort of to the left of minus 4, it's concave up. See how it's opening upwards. To the right of minus 4 and between minus 1, it's concave down, and then somewhere in there it transitions back to being concave up. So we've got 2 points of inflection. Both of them are non-stationary because it's not horizontal at that point. So we can print these things just from the graph. We can see these things. So let's get into finding f dash dash of x and drawing a sine diagram. So which one's going to be easier to differentiate? Here you'd have to use the product rule twice. Okay, you'd have to use the product rule for that, and you'd have to use the product rule for that. Albeit we've already differentiated that. So let's differentiate this. We are going to have to use the product rule here, twice as well, because we have to use it for that and then for that one. So let's not really going to matter. Let's just differentiate this one. So we've got f dash of x is 2x e to the x plus x squared e to the x. Okay, so this part here, we've already differentiated that. Okay, we differentiated that over here. We've got that part, we know what it differentiates to. It differentiates to this. So this part is going to 2x e to the x plus x squared e to the x. Right? That's what that part's going to. So we just need to focus on differentiating this part. And in order to differentiate this part, we're going to need to use the product rule. So u is 2x, u dash is 2, v is e to the x, v dash e to the x. And then I'm just going to smash it all into one. Okay? U dash v, u v dash. So just pause there for a sec, explain my thinking. So what do? We've differentiated this, that's that. We know the derivative of that goes straight here, so I've added them together. These are like terms, so bring them together, and I've just put the x squared term at the front there. Now, e to the x is common. And this part's going to have irrational roots, so we might use our, rather than using quadratic formula, okay, we could use quadratic formula, it might take a little bit long. We might just rely on our calculator to find the roots of this equation. So maybe it is a good opportunity to revisit it and just to show you how to do this question completely manually. So we're trying to draw the sine diagram of the second derivative, right? So we're trying to find when it equals 0. We've got e to the x never equals 0. Okay, so that means we've got this statement, x squared plus 4x plus 2 equals 0. So in order to find the solutions for that, I'm going to use quadratic formula. So that's minus b plus or minus, everyone should know this one off by heart. Beautiful formula. And so we're just going to crunch the values of a, b, c in there. We've got a is 1, b is 4, c is 2. Minus 4 plus or minus the square root of 4 squared, take 4 times 1 times 2, divided by 2 times 1. Okay, so I'm going to show you how we sort of simplify with some third operations there. 8. Let me detail this part. If you put the square root of 8 in your calculator, does anyone know what it's going to pop out as? Not what's the...
Root 2, root 4 or something?
2 root 2. Very, very good. Now, the reason is, root 8 is equal to root 2 times 4, which is equal to root 2 times root 4, which is equal to 2 times root 2. Okay, so in simplest form, root 8 is 2 root 2. So what we have here is we've got minus 4 plus 2 root 2 on 2, or minus 4 take 2 root 2 on 2. And so we're going to have minus 2 plus root 2 and minus 2 take root 2. Okay, they're the two values of x. They're going to be irrational. They're going to have an infinite number of decimal places, which are going to satisfy this quadratic equation. Now, if you did put that in your calculator, in your polynomial setting, have I got the calculator? No, I do. So let's do that too. So I'm going to go down to equation solver. That's the best way to do it. I mean, you can draw a graph. I'll go down to equation solver. Let's just focus on the quadratic. So it's a polynomial. It's a quadratic, which means there's two unknowns. Our value for a is 1. Our value for b is 4. Our value for c is 2. It tells me those roots. Look, minus 2 plus root 2, that's popping up in the bottom there. And minus 2 take root 2. And it's also represented them as a number of significant figures. So I've got minus 0.585. So if we're thinking of our sine diagram, minus 0.585 and minus 3.414. So let's make a connection here. Okay, let's make a connection here. Let's do like a little bit of working backwards. Okay. So anyway, if you were to evaluate that, that's the thing on 0.585 and minus 1. So we could do what we did before and put a number to the left and to the right and do that sine diagram manually, okay? Or we can anticipate what the sine diagram is supposed to look like, because we can see that point minus 3.41, let's just sketch that one, x equals minus 3.41. Okay, so that there is the point of inflection. Okay, and to the left of that point, you can see that it is concave up. Now, one thing we learned yesterday is if it is concave up, that means the second derivative is positive in that region. It's positive slope. The second derivative is going to be 0 at the point of inflection. We can see then in between x is minus 3.41 and x is minus 0.585. We can see in that region it's concave down. See how it's got that downward bowl shape? It's negative, and then it's positive. Okay, so if we're asked to draw that sine diagram, we can do it from the original function. You can see where it's concave up and it's concave down. You found these values, we found them exactly. Minus 2 take root 2, minus 2 plus root 2. And you only need to find them exactly if it says find them exactly. Alright, so yeah, this process here, I'm just demonstrating how we can do it exactly. But if you're doing this question in the test, you'll go, let's look it up on the polynomial solver. They're the solutions. Here's the sine diagram. Okay, we've done that. We've got the sine diagram. Let's make some statements. Hence, find the nature and coordinates of any points of inflection. So, I might rub out the quadratic formula part to finish answering here. Does anyone have any objections there? Okay, that year 10 maths can get out of the way. So, points of inflection, we've got at x equals minus 3.41, and then we need the corresponding y value. And this is where it's very helpful to have the calculator. Okay, so we've got when x is minus 3.41, y is 0.384. So I might write this as a set of coordinates. Minus 3.41, 0.384, and minus 0.585. The y value is 0.191. What kind of points of inflection do we have? Non-stationary. Okay, so we know that we can confirm that in 3 ways. Okay, I'm only going to explain 2 because the third one will just take time and be a waste of time. The first way is by looking at the graph. Where we see it transition, it doesn't go horizontal. It doesn't have a slope of 0. Right? So we see it transition at minus 3.41 and minus 0.585. It doesn't have a slope of 0. Okay, so that's the first point of affirmation. The second one is that f dash dash of x and f dash of x, none of their roots are the same. Okay, stationary inflection occurs when the second derivative and the first derivative have some value of x which has the same root. Okay, we don't have that occurring. They have completely different numbers on their thing. Okay, so because they're not the same, non-stationary. If one of them's the same, then that point is going to be stationary inflection. So they're the 2 ways we can affirm that. Okay, very last part. Hence state intervals when it is concave up and concave down. So it's concave up, 4. We've got x being less than. Okay, so I've answered the question exactly there, all right? When it says answer it exactly, it means in any surd form, as a fraction, without an infinite number of decimal places. What's powerful about it is it does include every possible decimal place. So this question here, right, it's not always going to be a pretty answer. And this is an example of when we don't have a pretty answer. Particularly for these parts here. Over there it was nice and pretty. You know, we had our coordinates as minus 2 and 4 on e squared. And over here you could take it a little bit further, but you've got, because this is an irrational quadratic, because the roots are irrational, this is gonna be a mess. So we just put it to 3 significant figures. And that's pretty well it. So that's a really good, like I've said, consolidation of what we've been doing. So 3b, we did when's it increasing, when's it decreasing. We looked at that over here. We looked at stationary points, and then we've covered again concave up, concave down. I reckon you would have found you've been doing a bit of that in question 1, 2, 3, 4. So let's proceed with 3D.1. Let's use our time well. do it.